most of the fun stuff's kind of hidden in my presentation. But I do want to start out saying, my close friend and piano teacher asked me, was I getting nervous talking in front of a whole bunch of people? And I said, I do get nervous so much, but I don't have to worry about it here. There's only going to be software engineer. So, a little bit about my background, because as I'm going to be making predictions about the future, you should at least know where I'm coming from. I've spent 50 years in software, and I started out writing actuarial evaluation programs. Then I went to real-time trading systems. I switched over from financial markets into the internet. I went to Amazon. I worked on their website architecture. More about that later. Spent 10 years at Google, designing a continuous computation system, kind of like MapReduce, but continuous. Right? It's pretty high scale. Does about 1.5 billion transactions a second very well. And then I went to Temple, where I am today. And there'll be a little bit more about that in the talk too. So I've been lucky to work on some of the largest systems in the world, both in terms of transaction value and in terms of the number of people using them. So I think that I feel like I've learned a lot, and I feel like I got something to say to you guys. This presentation, it's a little bit Dutch. That's not me, it's the presentation. It's, so I'm not going to try to cover everything that's in this topic, even though I'm going to be displaying the slides that contain information that we're not going to talk about. Honestly, that's in case you really like the subject. You can go back to the slides and review them, download them, review them later. The last thing I wanted to say about the talk, the meta comment, is that I'm not here to tell you things or to try to convince you of things. I'm going to give you my own impressions of things I've learned and hopefully spark ideas and thoughts for you. So why software organisms? This concept's been growing in my head for a long time and evolving. And, it started in a keynote speech I gave a year ago at another conference. I since developed it a lot, and I feel like it virtually gelled into something that's meaningful. So I thought it was perfect for this audience, especially for the closing keynote, because at the end of a conference where you've learned a lot, you also want to stop and go, okay, how am I going to carry this forward into the future? So I've been struck by the parallels between biological evolution and systems evolution. And it virtually surprising that there would be such, because they're driven by the same factors: scarce resources, competition, animals, organisms trying to compete for the same space. So I think there's things to learn from the comparison, and parallels it's part of how I think. I like abstractions and I like parallels because I can use one to look at the other and point out inconsistencies. I can use one to drive my thought process. So let's go back in time, just a little ways, 4 billion years ago, where there was no life on this planet. Okay, in biological time, that's 4 billion years. In system time, we're going to go back 50 years. This is actually the machine I learned to program on. I took my first class in high school. My high school didn't have a computer. That's not a computer, that's a teletype. All it does is let you dial in to a computer using that lovely phone acoustic coupler at 15 whole characters per second. And I closed in on the paper tape printer reader over there at the bottom right, because that's how you stored your program on this computer. You're to print the whole program out, 6-bit bytes, on a long roll of paper tape. You made one mistake, you had to reprint the whole thing. Loading your program took just the fun. It was great fun. There was actually one computer in my whole town. It wasn't at high school, of course. It was at the local college, and that's how we connected up to it. So if you think about the Earth at that time, there was actually one giant landmass. It wasn't different continents. And the ocean was full of biological ingredients, let's call it, amino acids and the building blocks of life, but no life. The computer systems at our time were about the building blocks too, right? The amino acids, if you will, of the computer world. So our primordial soup was really alphabet soup. So here's my first program, blackjack. And reading basic, we remember high school computer science teacher had never written a program before either. So we just sort of threw things together, tried to make it work. If they worked, we did it again, we copied them, we duplicated, like genes replicating, and if they didn't work, we threw them out and they died. So kind of like reproduction. So as we copied the things that worked and invented new things to try and see if they worked, and of course this is going on in the rest of the system industry, just really at this time, pretty much only in America. Progress was very rapid, because we had a lot of people trying new things all the time, and you just jammed it together, saw if they work. So we started getting things like at the hardware level modules and disk drives, and remember my first computer didn't have disk drives. New languages, new tools, the DNA, if you will, of software, and people started inventing things like data structures and error correcting codes and stuff like that. So rapid progress. And where did we end up? We started making cells, single-celled organisms, if you will, that worked, programs that did things that were valuable. Particularly valuable to me because I paid my way through college doing this. The hardware, the abstraction started to kick in. You did write to a disk. When I first disk write, we had to figure out how many bytes were on the radius of the disk so you didn't exceed the byte count, right? Then you pump outwards of the disk and you'd have a bigger disk so you could have more bytes on it. The abstractions changed everything. Well, it changed a lot, let's put it that way. Things became easier and easier because the abstractions became more and more powerful. We're going to hear that message over and over again in this conversation, so I'll try not to repeat it every 2 minutes, but the abstraction is important here. We also, during this period, this is like the 80s, started getting sorting algorithms, searching algorithms, graph algorithms, and for me, the most important abstraction ever, object-oriented programming. So I learned my first object-oriented programming language in 1987, I think it was. C++ came out, and that's what triggered me because I was writing in C. And I heard a talk by Bjarne Stroustrup, who was the inventor of C++. You didn't have a compiler back then. You just had a translator. It would translate your C++ into C. Then a C compiler converted to assembly, and you convert. Okay. So, fun fact, I had the very first copy, the very first C++ compiler in the world. Because I ran into the guy who's writing at a conference, and I said, do you want a beyond site? Because I was dying for object-oriented programming. The minute I got my head around object-oriented programming, I said, I'm never going to write code any other way. It changed the way I could comprehend what a system was going to do, how to organize it, how to make it do what I wanted it to do. Use slide. I'm going to call this, I didn't mention, I'm going to call this an epochal discontinuity. I wasn't the only one who just switched over to doing object-oriented programming when it came out the door. It really changed the world of programming, and it was the difference between before and after. So that was the end of an epoch. Before object-oriented programming, after object-oriented programming, I'm going to identify a couple of these today, and this one to me is the most important one. And I think they're valuable because you learn what is the kind of thing is a state change for systems design and for systems development. This was the first for me. So, single-cell organism still, it's a amoeba. Looks like a junkyard, a DNA junkyard for the single cells, right? So, we have, at this time, this is, sort of 90s, we have a lot of progress in computer science in terms of the algorithmic things, even things like Oracle's been built, database technologies have improved, network connectivity, the internet now exists, okay? So, I went to Amazon, and I found the largest single-cell organism of all time, so I actually gave this one a name, Amazonia obidosii. So, Amazon had 4 implication overdose. It was the entire website. One single binary, and pretty much all the code of the entire company, the whole company linked into it, because there was no dependency control within the code base or build system. And so everything just ended up getting sucked in by link dependencies into this giant binary. It was so big that developers couldn't link it on their desktops. It was really hard, almost impossible to run and debug. And I came to Amazon, saw this, and said, there's got to be something we could do about this. And of course, I'm Bradley with the company. I've been offered more or less a blank check by my boss, the vice president of software, Rick Dalzell, who trusted me. I said I could build something better. He said, go ahead, give it a shot. So he gave me a team. We started building a distributed operating system. A distributed website platform. I'm going to say website platform because it was actually a document generator. Okay, this was approximately my first drawing of that system. It was going to have templates that were executable. Okay, it was going to have a generator engine, which I'll tell you in a second. It was going to have services connected to databases. It was going to be, you probably know, a services-oriented architecture. It was one of the first. I don't even know it was. I'm certainly not claiming this first. I'm not claiming I invented it. I did, however, build it. I named it Groupa because the town of Groupa at the bottom left there, which is at the point at the Amazon River where the river spreads out into this delta towards the sea. And I thought of Groupa being an analog to that. It would take the request from the customer for a web page and it would spread it out across a whole bunch of services, and then we'd gather the information and display the page. Okay, and this, I think you'll recognize that this was an innovation that mattered. Okay, Amazon's architecture, their services-oriented architecture, these were the pieces we built. Okay, and they function. Some of them have been redesigned, replaced since then. What hasn't changed is the nature of the architecture. The service-oriented architecture of Amazon is still the same. And I think that it's spread pretty much across the world for companies doing this sort of application. The important part of the architecture is the abstraction of the service-oriented architecture. Independent services let you have teams decoupled from each other. It lets them deploy on their own schedules. It lets them separate concerns of the service from the underlying architecture, like logging errors and metrics and so on. It was the first time when we started thinking about the health of the system. There was no health of the overdose system. One process that either had crashed or not, and that was about it. And separation of business application logic. So all of this was like DNA. This is a new gene pool for computer system design and development, and it spread like wildfire. Okay, so this is my second epochal discontinuity, because it changed the way software is done, in our world of system design, large system design. I'm not talking about Microsoft Word. So I want to point out a couple of things here. My two epochal discontinuities, my two abstractions, object-oriented programming, that's in the coding domain. Service-oriented architecture is more in the deployment, the running domain, the system domain. Okay, they were complementary. They didn't talk to each other, so to speak. Okay, so both of them provided significant, huge benefits to the companies that use them, because they got their software done faster, they had more powerful, they had developers that were more productive and happy. They both gave rise to platforms, and they also gave rise to the cloud. Jeff Bezos literally called a meeting one day in 2003 or 4 and said, we're going to take these components, this architecture that's got services and stuff, and use it to sell services to the world instead of the website, right? Why not just use these pieces we built and sell it? Okay, that was sort of the birth of cloud. So I'm likening this to the Cambrian explosion, which, if you studied geographic history, geological history, is the period in time when in biology, we switched over from single cells to multicell organisms. It exploded, right? All sorts of creatures. The evolution just kicked into high gear, okay? And I believe that we pretty much see the same thing in our world, okay? That all the people here are representative of that, because you guys are all out there building systems, mostly based on service-oriented architectures. The SOA also created some monsters, my favorite, Megalodon. I was there at that time, and they kind of rule the earth, right? And the land, the sea, and to some extent the clouds. And but they have also they've expanded the ecosystem to allow for innovation that we're all doing. So that's my story up to today, right? I hope I didn't went too quickly, but my point of my talk isn't to look at the past, it's to use it to guide the discussion about the future. So let's go back to the future. But before we do, I have three takeaways about this past period that I've been discussing. One is that the most powerful thing in the world is abstractions. Okay, I believe that. I don't know if you do or not, but I can't think about cobbles without saying, all right, what abstraction does this fit into? How does this work at a fundamental level? How can I think about this problem? Because the problems are all freaking complicated. So if we're going to change the world in a big way, we probably have to create something new in the way of an abstraction to do that. Second thing I learned is that a bulldozer is much better than a shovel for digging a big hole, and your hands don't get nearly as blistered. If you want to dig a hole for the size of a building like this, you don't use shovels. So tools really matter, and it doesn't matter. What matters is if they're powerful and useful, not if they're theoretically correct. So everything is an abstraction, but the important things are. The last thing is that life expands to fill an ecosystem. But if you want the trying territory, you got to get there early. Okay, so now back to the future. Everybody know what that is? That's the big what ifs. What if we could have an abstraction for the purpose of your system? Okay, we're going to abstract its purpose. All right, too vague. That's where it started, right? Well, what is my system doing? It's doing work, right? Well, can I have an abstraction of work? Well, I can at least start to get my head around that. I start thinking about what work does my system do? What work do systems I know do? They create web pages, and they do airline reservations. They do, what's some of the good ones? They manage an entity object, like the customer is an entity object, right? Management, give them a new mailing address. This is starting to feel like something I can turn into a bona fide abstraction, so let's try. Well, if I'm going to have work, I want to unitize it. I'm going to have units of work, all right? So I'm going to define a unit of work to be, this is sort of a mathematical definition. Let's talk about it in English for a second. Work has to start, you have to do some stuff, okay? Probably it ends. I don't want to offend Mr. Turing, but you've got your hands around something now. If things are happening, those are like events and state transitions, right? Let's use that as our abstraction of work. So we start with nothing. We have to identify them, give them a key. Let's give them a state machine, okay? We'll talk about how that happens in a minute, okay? And then we have events. Okay? We're going to define completion because for humans, completed work is meaningful. And we're also going to define destruction because we want to throw things away when we're done with them. So my working glossary, right? Note the first rule of telling your own stories, you get to make up the names of the characters. I love making up names. So these are not anybody's names but mine. Now, obviously, I pick things that make sense to you guys, or commonly used for things that were commonly used. But if there was no name for it, I made one up. And you'll see that in just a second. So my work abstraction, I'm going to call that workflow. who does the work? We're going to create an abstraction called a worker. First worker implements the state machine. Makes sense? I want to have some sort of type system, but I don't want it to be too tight yet, at least. So I'm going to just give each workflow a type. It's a customer adjust change. Workflow. Now I can use workflow word now. It's an airline reservation workflow. So no more than an identifier. No inheritance, no connections to each other. But at least now I had our type system for workflows. It's whatever identified there. An instance of work. Right? This is critically important to my discussion today. If we talked about, if you've got classes, you've got some instances of other class, right? If you have work that has been started, okay, maybe completed, you need to I need a word for that. I'm going to call it a WEX. It's short for workflow execution. And if I need multiples of them, they're WEX-eyed, like hippopotami, right? So some other useful things. A workflow exists over time. Okay, things can happen, and workflow needs to know about them. If you want to tell a workflow about some piece of information it should care about, it care about because you're the programmer, you send it a signal, which of course has some data in it. And finally, we're going to call something a task, which is the processing of a state transition. We're not going to be talking about tasks too much, but I want it to be kind of complete. Finally, so we can talk about it, I'm going to call this workflow-oriented programming. I loved object-oriented programming. You knew I was going to go here. And then if you've got an architecture based on this, workflow-oriented architecture. So I'm over here to teach you workflows. I'm only here to nail the abstraction down so I can talk about the abstraction, because I'm all about abstractions. So, but a few things, it's just worth walking through a couple of things in your head to make sure that the idea is crystal clear. So, an event, you have to start a workflow. Something has to trigger the start of a workflow. They don't just magically appear. So, there has to be a starting event. Okay? And then the positive sync can proceed just like you'd expect. So, the abstraction is very clear there. Right? But you might want to ask, what's a workflow, what's not a workflow? And the answer is, it all depends on your perspective. So if you're writing some workflow code, and one of the things you've done is look up the data in a database, make a call to the database to get some data. That's not a workflow to you. It's a single line of code that did look up and got a value. When we've already described, we know what workflow is, that's not it. But on the database side, the receiver, the engine that's processing your query, well, let's see, query parse, query optimization, query path expansion, blah, 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 blah. Sounds a lot like a workflow. You don't have to have a workflow engine to have something that is a workflow. Workflow is a concept, it's an abstraction. So, last point. Workflows are composable and hierarchical. Right? You can take a bunch of workflows and jam them together in a box and say, the box of the workflow, okay, with a bunch of composed pieces. You can also say, I'm going to have workflow to plan my trip. I'm going to book a flight to Malaga. I'm going to book a hotel at Malaga. I'm going to write speech about Malaga in Malaga, right? So the container is the parent in this case, and the children are the subtasks, which are by themselves workflows. So workflows can be composed in many interesting and useful ways. It's very important to the abstraction. So we're going to include it. Okay, so where are we? We got this. I call it powerful abstraction. It applies to certainly a lot of real-world problems that, by definition of powerful, it's useful to a lot of different places. Widely applicable. There's nothing new here in the sense of what you can do. You could have written all this code yourself. We could have written your own workflow engine and then use that to do this, right? I'm here to say the abstraction is useful if it simplifies your work, makes your life easier, makes it understandable, etc., etc. I'm proposing the abstraction right now. Okay, so what's new is that I'm capturing this in an abstraction, but my abstraction's not done, so stay with me. One of the things to know, remember that I mentioned the object-oriented programming is about the code, and the system-oriented architecture is about the system, how it runs together. Workflows actually combine the two. there's the state that's encapsulated in workflow, but there's this concept of running workflow, out of which you get it waxed. And that's part of the abstraction. And it's going to turn out to be, that's a very useful thing. And we're going to talk quite a lot about that in a few minutes. So, it's always nice to have one crystal clear example that you could use and everybody understands it. You could throw it at people and they'll throw it back. So I'm going to use a bank transfer. Okay, it's going from some account to some account with some amount of money. Okay, it turns out that this is a account-get-paid program in the real world between two banks. And we're going to see some of that complication in later examples. The most interesting thing about this is everybody understands it. So that's my bank transfer. Okay, think about a group of transfers, right? A batch of transfers. It's kind of like a living being. You start it, and all the transfers run. Okay, and then the whole thing ends. It's got a birth, it's got a death, it's got changes in its life. I'm going to call that a workflow organism. And work. The fact that it's a feature of the abstraction means that I can control it. I can start them, I can stop them, I can interrupt them, I can debug them, I can get statistics about how long they take, I can compare this organism to that organism, I can extract both control plane information about the organism and data plane. I can ask what's the largest transaction, what's the largest amount in this animal, in this work. So, I can create dimensional collections across more than just what the programmer said. The programmer might have created a batch of these transactions, but the system can create a work, a collection of transactions like all the transfers that happen in the 2 o'clock hour. But now we can treat that as an abstraction. We can get statistics about all the transactions that happen in the 2 o'clock hour. Even if the actual stream of transactions is continuous, we can impose a collection on top of it, which creates a workflow, which is a part of our universe here, and now we can manipulate it with our system. For me, this is very powerful. There's also all sorts of processing abstractions that make sense in the opinion of workflows as an abstraction. And I'm going to work through one of them in great detail. I'm going to skip the rest because we don't have time. But if you ever feel like it, you can either ping me out email or you can just work it out for yourself. So here's my little example. We got a batch of transactions like we've been talking about. 1 million of them, right? They're just transfers for one bank. And the bank have to process these transactions. This, by the way, isn't even imaginary. It was one of our customers that I think doing this exact design right now. So, but there's a rule. Any party who's sending more than $1 million have to be approved by a human. Okay? So, this is not a non-trivial problem in most architectures to design a solution to. You're going to see that with our little abstraction here of workflows and WEX and so on, that it's pretty trivial. And that's what an abstraction is for. So we've got a starter. It's going to take 1 million transactions out of a file, and he's going to start them. 1 million. So, but he knows they have to wait to do. Remember, I need to know if anybody's sending more than $1 million. That means I have to collect all of the transactions that I'm sending Paul and then make sure that Paul's transactions are more than $1 million. And I have to do that for everybody. So he created something I call a two-phase wait group, which is one of the abstractions that is implied, if you will, by...
He said, to make a nullable agreement that is
multiple transactions for one person. This is, I just said sending, just as my example. So he wanted to know if it was both sending and receiving, and if it was per person. So I clarified that, and it is. It'll become more clear in a second to be right on the screen. So, and the weight group knows that there's 1 million transactions. Because the starter told it that. Exactly 1 million, right? So now the starter starts some transaction. There's 6 of my million, right? And the transactions start processing. They send $100 to Paul. I'm sorry, that's Paul sending. Paul's sending out $100, okay? Paul, the workflow, that A stands for authorizer. That's the authorizer for Paul. We've constructed it on the fly based on the data. So now there's a Paul authorizer, but he has to wait till he has all inputs before he proceed. That's what this wait group is for. So he joins the wait group. He waits on phase 1 of the wait group. And that's what that W stands for. So, and we say that Paul sent $1 billion. They'll think that's going to get authorized. $1 billion. Okay? There we have Sergey. He decided to send $450 to it. I just wanted another person in the puzzle here. Okay? And he also has to wait. That workflow, the authorizer for Sergey has to wait. They're both waiting for all the other transactions to complete. So their inputs are complete so that they can either authorize or not. So that transaction completed, that transaction completed. We keep completing transactions until they're all done. The wait group knows this because this is what it's designed to do. And then it sends a message to the Sergey authorizer saying, go ahead. And it sends a message from the constant, just go ahead, do your work, okay? Same thing to the Paul authorizer. Paul rejects it by sending a message to his transaction. Sergey says, go ahead. And now, remember that the transactions themselves had to wait. That was the phase 1. They're waiting for phase 2. So now that the Paul authorizer and the Sergey authorizer are complete, they close their wait group, and everything completes. Okay? The thing is that, given the abstraction that we were proposing here, this is just a few lines of code. It's really simple, straightforward code to implement something that is really quite challenging in a traditional architecture. So I consider this to be so big, I called it WORPR. Workflow-Oriented Programming Runtime. Also a computer system from a famous old movie. What we're really going to, if we're going to turn this abstraction into a useful system, what we're really doing, if you think about it, is we're creating an operating system for this kind of work. And because there's a processing model, it's very much like an operating system. Unix runs, Linux runs, system processes, just executables. This WORPR runs workflows. But it's not limited to workflows, and there's nothing that prevents workflows from interacting with other systems. And if it's going to be a complete operating system, it's going to have to do that as well. So the operating system is going to take care of care and feeding of the works, the hierarchies, understanding them, visualizing them, giving you tools to do debugging of errors and so on, and interacting with other services. I'm going to skip more operations because I'm out of time. And just close off with, my impression of today's cloud is every system's one-off. It's an integration nightmare. The knowledge you need to set up Kubernetes, to set up the Helm, to set up the all of the metering, and then manage the damn thing is gigantic and offensive. And I believe that this workflow abstraction, workflow-oriented architecture, is going to lead to I'm not going to call it cloud because that's not how I see it. I see it as more of a systems community where, depending on what kind of application you're running, you're going to have different tools. Obviously, I'm proposing that if you're writing a tool solving problems using workflows, you're going to have very powerful tools, so that's going to be a valuable thing for you to do. And I'm also going to call this my epochal discontinuity number 3. I believe that this is going to change the world as much as object-oriented programming did in that way. As much as service-oriented architecture had a lot to do with that, I feel good about that prediction. And it's going to give you an enormous amount of new power and productivity in the future. So finally, I wanted to say thank you. for giving me your time, for listening to my spiel. The opportunity was enormous for me. I really appreciate this. And I really hope you find some of these ideas useful, either in actually writing systems in the future, or just in thinking about how you're going to write future systems in the future. Type the Q&A.